I'm delighted to be here and to share my thoughts with you. This is work that I did with three of my colleagues at Carnegie Mellon, Nathan Beckman, Grace Lewis, and Brandon Lucia. And really, it, it was a set of questions around a problem that dates back to the dawn of mobile computing, almost 30 plus years ago. Um, we observed that mobile devices of that time could not be too powerful relative to the service of that era. They had to be small, they had to be lightweight, they couldn't get too hot, you needed to have battery life that was decent. So all of these things were challenging for hardware designers. And the result was that in 1993, when this observation was first made, if you looked at a laptop, which was the only mobile device around at that time, and you compared it to a server, there's a huge gap. Fast forward 30 years roughly, 25, 30 years roughly, and the story is the same. And in fact, if you look at the evolution of mobile hardware and server hardware, and the paper gives the details of how exactly we calculate these numbers, etc. In the short talk, I don't have the time to go into the details. What you see here is the green bars show the typical server every few years. The red bar shows you the typical smartphone form factor, so portable, but not wearable. And then the blue shows you the wearable, top of the line device of that era. So you can see there's a huge gap. That gap has continued. And for the foreseeable future, it's going to continue. Okay? So here's the problem. As users, we have superb connectivity on our desktops. We have great compute power from them. And we're used to a certain level of performance and functionality. And we want it all. We want that capability on our mobile devices. I want speech recognition no matter where I am in the world with my smartphone and so on. And so this gap between what mobile hardware can actually deliver and people's aspirations, desires for what they want in terms of functionality, that gap is large, continues to be big in spite of Moore's law, in spite of improvements of the mobile hardware. So the question is, what do you do? How do you reconcile these two things? So the path to how to reconcile this was actually shown somewhere around 1997 in this paper that was written by Brian Noble, Jason Flynn, and a number of others. And it basically showed how you can do speech recognition. Remember, this is 1997, and the hardware on which this ran was, by today's standards, pretty pathetic. And yet, by offloading computation from the mobile device to a remote server, you could actually get decent performance for speech recognition. And there were many approaches to doing this. You could do part of the work locally, ship the intermediate state, complete the work remotely, etc. And you can find all the details in that paper. So these ideas, this general approach was generalized as a technique called cyber foraging, more commonly today known as offloading. And it's a standard technique that's used by many, many mobile devices. Every time you use a piece of functionality like Google Goggles or various kinds of functionality for speech or natural language processing on your smartphone, this is indeed what's happening. One of the questions that arose very early was where should we perform the offloading? Who's going to provide the infrastructure for this? And the emergence of the cloud provided the perfect answer. And in fact, the very first commercial speech recognition on mobile devices, which was Siri on Apple devices, did precisely this. And speech recognition on Android devices does something similar. And in general, this all is standard practice today. Of course, as Christine pointed out in her introduction, about this time we observed that you needed to be able to do this offloading at low latency. And so edge computing today includes a compute capability that is closer to the cloud in terms of capabilities, in terms of power, but physically and networking wise, close to mobile devices. So you have the low latency and high bandwidth to the devices, but you have the compute power of the cloud. And this intermediate layer, by the way, is often referred to as a cloudlet. So this model of computing has emerged. This is now something that is being rolled out by various parties as we speak. And so all seems to be good. Completely independently of this whole line of work is a completely different approach to solving the mobility penalty. And this is to make the mobile device itself much more powerful using application-specific integrated circuits. So Apple's neural engine, for example, which came out about 3 or 4 years ago, 2017, if I recall correctly, already had chips in it that allowed it to perform amazing core AI algorithms. Qualcomm's Snapdragon neural processing engine does something similar. There are companies now. Desi is a company that is creating custom hardware for this kind of application. The folks from Stanford, Chris Ray, and I forget his co-founder, have founded this company, Samba Nova Systems. And in academia, there's been a lot of work on this. So Nick Lane from Cambridge University is perhaps the most prolific person in this space, designing various kinds of ASICs for basically AI algorithms of various forms on mobile hardware. And Bill Daly, who's a professor at Stanford and also the chief scientist of NVIDIA, just about 6 months ago, had a very nice article in CACM on domain-specific hardware accelerators, precisely this issue. So the question that I'm addressing in this paper and this talk is, given that there's a new approach to solving the mobility penalty, do we still need the old ways? Do we still need edge offload? Sometimes in history, there are technologies that were useful when they were needed, but then later on, they're no longer needed. You just move on. So is it the case that offloading is one of those things? Maybe the future is ASICs. And in fact, if you notice, very recently, Apple announced that, in fact, they would no longer use x86 hardware in their chips for the future, that they would, in fact, be custom building their own chips. This is a public announcement by Tim Cook. So these are all pointing to a world in which custom chips on mobile hardware are going to play a very, very important role for the future. So to understand what role, if any, edge offload can still play, let's just take a step back and ask, what is edge offload good at? What are ASICs good at? And is there a way their strengths can be combined and the weaknesses neutralized? So the huge win with edge offload is that there is absolutely no custom hardware development. This is huge. And the reason it's huge is essentially conveyed by this graph at the left, which is from the keynote talk given just 2 years ago, on the fact that NRE stands for non-recurring engineering costs. This is sort of, even if you produce one chip of a new kind, you have to pay this big constant cost. And it's in the hundreds of millions of dollars. Depending on the feature size, the cost goes up, but even the sort of the lowest end of this is very, very expensive. In contrast, software can be written in a garage or wherever, in a dorm room. So there's a huge difference in the cost and the delay in terms of time for creating this software and of change. So Agility, cheap, easy, fast to produce, all of the attributes that surround these positive aspects of software make edge offload very attractive. And in a funny way, it is worth remembering why Intel invented the microprocessor. 40 years ago, in fact, more than 40 years ago now, 1971, it's almost 50 years, um, Intel was faced with the need to produce 4 different chipsets for 4 different calculators by 4 customers. And they figured out that it was going to be far more sensible to produce one chipset and use software to precisely create the functionality needed by their 4 customers. In fact, that's how the Intel 4004 microprocessor was born. So here is a real fact on the ground that the value of software lies in its agility, in its speed of, and its ability to change and morph rapidly relative to hardware. And that is true with edge offload as well. Secondly, any new hardware that you introduce into the world takes some time to penetrate. It doesn't become widely used overnight. So the ability to support devices that do not have the unique hardware is something that edge offload can do for you. So for the new devices, you use the ASIC. For the old devices, you use edge offload. The user of the application just sees the system working. He or she doesn't see that the implementation under the covers does something different. Now, of course, there's a double-edged sword. Um, if your application runs on the old device, perhaps there's a disincentive to buy the new device. So in the marketplace, exactly how to navigate this, how to make it not be too comfortable a zone to live in forever is something that hardware vendors certainly need to deal with. But on the whole, the ability to support legacy code, legacy applications, and legacy devices is a big win in terms of edge offload. Obviously, in mobile computing, battery life matters a lot. And here is conceptually the trade-off space that is relevant to this talk. On the x-axis are the size of the inputs and the outputs. If you're going to offload, this is the amount of data you have to ship to the server and the amount of results you'll get back. On the y-axis is how intensive the computation is of the procedure or functionality that you're offloading. Clearly, if you have very small results and operands, but you have a tremendous amount of compute, clearly doing the work on the server, offloading wins big. So that's the top left corner. If the polarity of these attributes is reversed, then the bottom right corner becomes important. So there is a space here for which offloading is valuable, and the space above the dotted line is in fact the zone where edge offload wins. And so there is a role for it there. Finally, today, most applications that are worried about latency have some kind of target latency. So for example, for augmented reality, 16 milliseconds has been shown to be an important number in terms of deeply immersive augmented reality. For other applications, you can measure the human performance, the point at which human performance starts to be noticeably degraded, and the point at which the user decides, I can't use this system anymore. And making the system faster than the the shortest latency that the user actually perceives, there's no point in doing it. So that all of these systems have a target latency. But there are applications in the pipeline which don't have this limit. So think of any kind of adversarial setting in which you and a competitor are both relying on offloading, but the one that is able to obtain more compute in the same time is able to search a bigger space or explore more options and come back with a better optimum solution than you. You have the edge on the competitor. So in these kind of settings, which are adversarial rather than cooperative or targeted, you have a huge win from being able to offload. So those are some of the strengths of offloading. Let's look at ASICs. Well, the single biggest win is it works everywhere. You don't need a network, you don't need cloudlets, you don't need edge computing, nothing. So ubiquity and disconnected operation, which you all know is dear to my heart, um, are clearly supported by devices that have ASICs. If you're looking for the ultimate in latency, no longer 10 milliseconds, but maybe 1 millisecond or sub-millisecond, it starts getting harder and harder to do it if networking is involved. There's a whole community called the Tactile Internet Community. They're working on sub-millisecond RTTs, but this is a big lift. It's very, very difficult. Achieving these kinds of end-to-end latencies without offloading, if you can have an ASIC, is a much easier task. So in the most deeply immersive, most latency sensitive applications, it is going to be the case that ASICs are at an advantage. Something that is very important from the point of view of deployability is how scalable is your system. If I have to invest in a huge amount of infrastructure, edge infrastructure, so that your application can run, that's a very expensive application to deploy. If, on the other hand, your mobile devices are able to execute almost all of it locally, and only perhaps exception handling has to be done remotely, or a small number of fraction of the operations have to go remote, you have a much more scalable system. In other words, to the extent that most of the compute burden of your application is borne by the device and not the infrastructure, you have a much better edge on scalability. And this is an old point which has been made basically at the dawn of distributed systems. It continues to be true today, and ASICs do support that. And last but not least, going back to a figure about energy and offloading versus ASICs, remember that dotted line that I showed you that separates whether it is more profitable to do it locally or remotely? What ASICs do is move that line very substantially upwards. In other words, there are many, many, many more settings in which it's more profitable to do it locally because you now have the hardware acceleration. So the last point here has to do with the fact that whenever you offload, you have to trust the infrastructure, so your TCB enlarges, and the very fact that you talk to the infrastructure means your presence becomes visible. So if you're in the covert operations business and need stealth, then not being able to use the infrastructure is a big win. And certainly in terms of trusted computing, only having to rely on your mobile device is a big win. So these are the sort of strengths and weaknesses of these two approaches. And the question is, how do we go about combining them? So the hint, the insight, comes from recognizing that you can look at an ASIC almost like a complex instruction, because it's performing a very unique function for that application. So somewhat similar to all of the special instructions that people try to create for hardware architectures. And the RISC versus cisc debate has been going on since the late 1970s, as far as I know. So we have, half a century of learning and insights which we can build on in trying to think about this. And there are two particular insights that are valuable. One was actually made by Jerry Salzer, Dave Clark, and Dave Reed, I believe, in a paper that I bet almost all of you have read, which is called the End-to-End Arguments paper, which is published in 1984. And Jerry Salzer and company say that basically the RISC argument is that the client of an architecture will get better performance by implementing the instructions in software Basically, this is the equivalent of offloaded. Any attempt by the computer designer to anticipate the client's requirements for an esoteric feature will probably miss the mark slightly. And once you do that, the client has to re-implement that in software anyway. In other words, if you are so good and so prescient that you can precisely target the ASIC, you win, no question. But your aim has to be amazing. The chances that you will get it right are not that high. And almost always, based on past experience, compilers have ended up generating low-level simple instructions rather than using cisc instructions because, in fact, they miss the mark slightly. So this is a valuable insight to keep in mind as we think about ASICs. And there's a second comment from John Koch, who won the Turing Award for the invention of RISC technology in 1990. And he makes the observation that even if qualitatively everything looks good, don't believe it. That in fact, until you do the trace-driven simulation or trace-driven analysis based on the actual sequences of instructions, your intuition is likely to be wrong. So the key insight here is figuring out exactly what an ASIC should do, not at a general level, but at the precise specification of operands and details of execution. That is the hard part. And especially when your application is changing rapidly, either because you're just figuring out what the application should do, or because your competition is forcing you to change, for either of those reasons, doesn't matter which the reason is, it is very unlikely that your first try at an ASIC is going to be right. And so the lessons are from Salzer's and John Koch's advice. Don't even try to design the ASIC until the application has stabilized. And even then, don't believe that the ASIC you will design will actually provide a win. Use actual traces from execution, perform the trace-driven simulation, and verify that the expected savings in energy and runtime actually happen. And so the underlying assumption that a designer's intuition is going to help here, this is one of the quicksands in which many a bet of this kind has been lost. So there's a middle ground, which I don't have too much time to spend on in this talk because I'm starting to get to the end of my talk here. But in the paper, there's a fair bit of discussion about an intermediate ground in the form of programmable accelerators, things like GPUs or FPGAs, which kind of are a middle ground in terms of flexibility versus speed and energy efficiency. So this slide basically is a summary of the paper. What do you do? How exactly do you combine these? So here's the basic approach. There are three lines here, and this is time flowing from left to right. The topmost line is the evolution of the application. This might be an augmented reality, natural language, some really innovative, exciting application. At the bottom is the specialized hardware, the new ASIC, that is going to make this possible to run on a mobile device without any offloading. And then in between the programmable accelerator line is the software that is needed to, typically on the offload engine, on the cloudlet, for example, to provide the speed when you're offloading. Typically, a lesson that has been learned over the last 5 years is edge computing requires GPUs at the edge or FPGAs. You can't do it just with CPUs. That the order of parallelism that you need is at least 2 orders, maybe more, higher than what CPUs typically provide you. So the evolutionary path is shown here. You start out with an application, you use edge offload, you use GPUs or other accelerators on the cloudlets to provide you with the necessary high degree of parallelism. That software goes through many releases, much evolution over a period of a year, 2 years, whatever period of time. At some point, signified by A2 in the slide, the application stabilizes. And from this point onwards, its evolution is slow. This is the point at which you can actually capture traces. Those traces are stable. You can design an ASIC, create a simulation-based evaluation of it, ensure that the win is large enough, and create the first ASIC, C1. You might need to go through some versions of it to tweak it. So C2 is the final version of the ASIC as produced. And then you need to build a mobile device that actually integrates it, that C3 at the bottom. And once you have that, you then have application A, which no longer needs offloading. For some period of time, you'll still support offloading for that application because of the need to support legacy hardware. At some point, you end of life that, and you now have that application A, which is able to run on the mobile device. So the total time duration is on the order of years, not weeks or months, because that is the time duration for producing custom hardware. And equally importantly, also for the first part of this evolution, namely the stabilization of the application to actually happen. And then you need time to analyze it. So if you were to ask my guess as to the length of this timeline, I would be surprised if it's less than 5 years for a given application. So hopefully, I've given you a, a way of thinking about ASICs and edge offload that is useful. The paper has a lot of other details that I don't have time to cover, some implications for business models, what kind of tools might be useful. And I've shown you the canonical model. There are many variants that are possible. And as I mentioned earlier, programmable accelerators um, are an important sort of a halfway house between the two extremes, and the paper discusses their role. So, closing thoughts. If you look at human beings, look at all of us on this call, we perform amazing perception and cognition. The accuracy level, the speed, even under very difficult conditions, our software doesn't even come close to this today. And we've been at this now for a few decades. But notice that human beings don't do offload. We have no cloudlets anywhere. We function as totally autonomous entities. So we are living proof that creating ASICs, creating completely mobile devices that don't depend on any external infrastructure is indeed possible. So we are the proofs of that feasibility. The reason this is possible is, of course, the ASICs in our brains and our nervous systems that have been tuned to these amazing feats of perception and cognition. Here's the catch. Nature took 1 billion years to evolve those ASICs. We don't have 1 billion years to wait. We want to try and build improvements on nature in the order of 10 years, maybe 100 years at most. Most of us will be dead by then, but at least civilization hopefully is still around. But that's 7 to 8 orders of magnitude speed up over nature. Now we are clever, but not that clever. There's no chance that if we have to play by the same rules as nature, that we can actually improve upon it. Think of offloading as a way of cheating. You are able to create applications that require infrastructure, hardware, that is far larger, far heavier, far more heat dissipative, and far hungrier in terms of energy than you could ever carry with you. But because you're able to offload to the infrastructure, you're able to run those applications on very lightweight mobile devices. Once you do that, everything I showed you in the previous slide on the evolution of that functionality and the development of ASICs becomes possible. And so the way to think of edge offload is that it provides the path to discovery of new applications as well as new ASICs to support those applications and to optimize them. Thank you.